So allow me to share my screen. What you can see, class, is the exact PDF copy of Module 2. Okay, so I have shared in Canvas under the lesson for Module 2 the entire set of topics for techniques of integration. And we are now continuing this afternoon on integrals involving complicated trigonometric functions. Now, these integrals that are said to be involving complicated trigonometric functions require, class, that you do trigonometric transformation prior to applying the previously learned concepts on integration. So what are these previously learned concepts on integration that you can apply after you have done transformation to these complicated trigonometric functions? So you can either use power rule, you can either use substitution, or even you can use the formula of integrals yielding the natural log function or the natural exponential, no, not the natural exponential function, the natural log function, and other techniques that you will be learning later on. If you're going to check in books on integral calculus, this topic on integrals involving complicated trigonometric functions is named as trigonometric transformation. So if you have textbooks in calculus, it's a topic under trigonometric transformation. Okay? So for this afternoon, actually there are, if I'm not mistaken, there are 7 types or 6 types under trigonometric transformation. So the others are just a combination. 7 types under trigonometric transformation, meaning 6 types of integrals having complicated trigonometric functions, which requires that you do transformation before you apply the appropriate formula for integration. Okay, so again, I will emphasize that you will find this topic in books labeled as trigonometric transformation. Okay, now under type 1, so under type 1, remember we have 6 types. So under type 1, you have 2 cases. So that's case 1 and this is case 2. Now that's what we're going to cover this afternoon. What is type 1? So these are integrals having the sine function or the cosine function raised to positive integer, meaning it has to be a positive whole number, this n here. Now case 1 is when n, this n is odd, while case 2 is when n is even. Again, so case 1 or type 1 is for an integral evaluating a sine or a cosine function raised to n. And n is a positive integer. So positive integer meaning you cannot have a fraction, you cannot have a negative exponent for the sine and cosine. So we have 2 cases under this because this positive integer class can be odd in the case of case 1 and it can be even in the case of case 2. But they are both, of course, under type 1 because they either involve a sine or a cosine function. Now, let's look into case 1. How do you deal with an integral having a sine or cosine raised to a positive odd exponent? So, positive odd exponent. So, the suggestion here is you split. You split your sine or your cosine, setting aside, you set aside one sine or one cosine, and the other part is, of course, raised to an even exponent. Since it is odd, you take that particular one function raised to 1 and then the rest of your original function will be raised to an even exponent. Then what would you do with that particular function that is raised to an even exponent? You use its equivalent identity. Now, you've learned in your trigonometry in high school that sine squared x is equal to 1 minus cosine squared x. So if you're dealing with a sine of x raised to n, you split it into sine of n minus 1x times sine of x. If you multiply these two by rules of exponent, you will have sine of x raised to n because you will add the exponents of the sine in here. Then this one, the part that has an even exponent, you convert it to the cosine equivalent using this particular identity. Why do we do that? It's because if you distribute the sine of x later as a multiplier to this 1 minus cosine squared x, this one will be integrable because it would become sine. And your cosine function here can be processed using the power rule because by rules of substitution, the derivative of your cosine function here will be this particular sine function. So then you will use power rule on the entire cosine function. Now to illustrate what I mean, I have here two examples for a function that is raised to a positive odd exponent. So our first example is for cosine cube x. So split the cosine into cosine of x and cosine squared of x. Okay? Now, if you multiply these two, you go back to the original given function, which is your cosine cube x. Then what you do, you convert the cosine squared x to its equivalent, which is 1 minus sine squared of x. I'm sure you fully know this from your high school. Why do you need to convert the cosine squared of x to 1 minus sine squared? Because you do that because after you have converted the cosine squared of x to this equivalent identity, you will multiply it with this cosine function which you have set aside. So when you multiply it to the cosine function, the first term will be the integral of the cosine of x dx, and the second term will be sine squared of x cosine x dx. Now, if you look at it very closely, this will be comparable class to u raised to n, and this will be the du. The du will be the entire cosine of x dx. Why? Because your u here is the sine function. Sine of x. So the du of that would be cosine of x dx. It's being raised to an exponent, which is 2. So it's like that. So your u raised to n, where u is sine x and n is equal to 2. So then you can have this integrated. The cosine function, when integrated, gives a sine of x. And this one will be using power rule. I'm referring to the sine of x squared. So since you have already its derivative here because it's u raised to n du, then this n becomes 3. And you will have to divide by 3. So it becomes sine cube of x over 3. So this is now your answer. This is your answer for the original integral of cosine cube x after you have done trigonometric transformation. So this entire process of splitting the cosine into a cosine which has an even exponent and a cosine of x is part of the trigonometric transformation because still you need to convert the cosine squared of x to 1 minus sine squared x. Now, in principal class, you follow the same procedure when we talk about or when you're given a sine function which is raised to a positive odd exponent. Now, I'd like to clear my markings here if there aren't any questions anymore. I'll proceed to sample number 2 under case 1. Do you have any questions? Okay, so there's none. So I'll clear my marking here. Oh, John? Yes, John.
Miss, where nag-get ang negative 1/3 ganito?
Power rule. Power rule.
Okay, miss.
Your u raised to n is your sine squared of x. So your u is sine of x. Your du is cosine of x dx, your n is equal to 2. So by power rule, your answer for this is u raised to n plus 1 over n plus 1. Since your n is 2, so you have here a 3. And this is also a 3. Do you get it?
Yes, please. Thank you.
Okay. Now you do apply the principle as well to sample number 2. So you split this sine of x raised to 5. You set aside 1 sine x. And of course, you have here sine x raised to 4 to make it sine x raised to 5. Okay? Now, you convert this sine of x raised to 4 to 1 minus cosine squared of x squared. Why is that? So allow me to write in here. Your sine squared of x when squared is equal to sine of x raised to 4. What is the sine squared of x? That's 1 minus cosine squared of x. That's your sine squared of x. Then you need to square it because it's being squared. So that's what happened here. This is your sine which was set aside. Now you cannot have this evaluated with the sine of x dx here unless you expand if you're going to use power rule or the simple integral of simple trigonometric functions. So you have this expanded. How do you expand this? Your algebra taught you that. So 1 minus twice the product of this. So you have 2 cosine squared x plus cosine of x raised to 4. Cosine squared x squared is cosine of x raised to 4. Now, if you will distribute the sine of x here as a multiplier, so that would be like this, and you have like that, and you have this. Okay? Now, if you look very closely, this sine of x dx when multiplied to 1 will be itself, and when you integrate, that would be the negative of cosine x. Now, just like the first example here, this negative 2 cosine squared of x times sine x will be processed using power rule. So how will you process it using power rule? Your cosine squared of x is comparable to u raised to n, where n is equal to 2 and u is equal to cosine of x. The du of this is negative sine of x dx. Now, this is actually power rule with substitution. Why? Because this entire cosine function will have the derivative negative sine of x dx. And this sine of x here, dx, that is being multiplied to it together with this negative sine will be the derivative of this cosine when you process it using power rule. So that's the reason why you have here positive already, because this negative sign was paired with the sine of x dx to represent the derivative of the cosine of x. Now, if you process cosine squared x using power rule, you add 1 to its exponent. So you have cosine cubed x over 3. Just like this one being n, so you add 1 to that, so this would be 3. And this would also be 3 because whatever is the exponent of the function which you use power rule, that would also be the denominator of that function. So you have your cosine cube x over 3. This 2 is this 2 in here. It's a constant, so it's just there. It's being multiplied to the answer of the function cosine squared of x. Now, what about this one? The cosine to the fourth of x times sine x. The same way as you process this. Okay. The only difference of this one from this is the exponent. So you just add 1 to that. So since the derivative of the cosine is negative sign, so this is positive. So that is why you see this one as negative. Because you're going to introduce a negative sign here and there will be negative sign in here. But as to power rule, the new exponent of cosine of x raised to 4 will be cosine of x raised to 5. And then, of course, it will be divided by 5. This is how we apply case 1 under type 1 for trigonometric transformation. Do you have any questions so far in here? Okay, so I will proceed if there aren't any questions so I can finish the case 2 under type 1. So case 2, your exponent n is also positive, but this time it's even. Case 1, it's odd. So what identity will you use to transform your cosine or sine function, which is raised to an even positive integer? This will be your new trigonometric identities. You will convert the sine squared of x and the cosine squared of x to its equivalent identity containing the double angle cosine. The only difference between the sine squared and the cosine squared is the sign that separates 1 and cosine 2x in the numerator, but the denominator is the same. So for sine squared x, it's minus. For cosine squared x, it's plus. Okay? Now, having said it that it's a double angle cosine equivalent of this sine, the term double angle, whatever is your angle here, it is being doubled here in the equivalent identity. Now, how are we supposed to apply that particular principle to any particular angle here for a sine or a cosine that is being squared? So let's say, for example, you're given sine squared of 1/2 x. How will you write its equivalent double angle cosine identity? So remember, you are to double the angle, and this is the equivalent identity. If it's x, so it becomes 2x here, it doubles. So the same thing with this. You just simply write here equal to, the denominator is still 2. You have 1, it's still 1 here, minus, it's still minus. The cosine of, you double this. So this is x. So whatever is your angle here, it's being doubled in the cosine function that is equivalent to it. So we call it the double angle cosine. Okay? So don't just simply memorize a formula like this without understanding why it's like this. So if this one is x, this becomes 2x. If this is 2x, this becomes 4x. Why? Because the angle or the argument is being doubled. Okay? Now we will go to our example. So for our example, you have here the sine squared of x dx. So we convert by using the identity that we have here. Next is we split this into two terms in which 2 is the denominator. So if you're going to process this, that's 1/2 x. If you're going to process this, your u here, this is equivalent to the simple trigonometric function cosine u du. However, du means the derivative of the u. And what is the u of your cosine function here? It's 2 dx. So meaning your du should be 2 dx. You lack 2 in here, you divide 1/2 in here. So what happens? Your original 1/2 here will be multiplied to another 1/2 because you need to introduce this 2 in the derivative dx. That way it will complete the derivative of the u of your cosine function to 2 dx. So that is why you see here already 1/4. Because your 1/2, this original 1/2 here, this 1/2, times another 1/2 due to the introduction of 2 in here. So that would be 1/4. What's the integral of cosine? That would be the sine of 2x. So you copy. This is actually under simple trigonometric function. Sine of x is cosine of x, or sine of u is cosine of u as long as the derivative of the u is complete. Okay, so our answer, okay, my things. our answer here will also constitute two terms. 1/2 x for this one, or for this, and 1/4 sine of 2x for the integral of cosine of 2x dx. So this two class was just introduced. So actually, there was another multiplication here by 1/2 to make it just 1. So that is why you have here 1/4. Okay? Now, if we have the double angle cosine, in the case of cosine of x raised to 4, you notice here it's 1 plus cosine 2x over 2. We double the angle here, and it's plus because it's cosine. Here it's minus because it's sine. It's being squared because this one is actually equivalent to the cosine squared of x squared, to make it cosine of x raised to 4. So this is the reason why you have here 2. That requires that this is to be expanded. There's some error here, class. This should be 1/2 squared should be 1/4. So this should be 1/4, not 1/2. And you will have this expanded to 1 plus 2 cosine 2x plus cosine squared of 2x. If you will distribute the 1/4 here to the three terms, 1, 2, 3, so all of this should be 1/4. So this should be 1/4, this should be 1/4, this should be 1/4. Okay, there was an error there. Now, your 1/4 times 1 will give an integral of 1/4 x. Now, this becomes 1/4. This is 1/4 times 2. So that would be 1/2. So by the way, that would be only 1/2 cosine of 2x. However, class, you see this? You have a 2x here. So its derivative is 2 dx. So then it's still 1/4 here because you need to place 1/2 before this integral for this one. So it's still 1/4, or by the way, if I will have this written here, right ha? So you will see, para clear. You will have here 1/4 dx, okay, for that one, plus, if we use these two as the derivative of this 2x here together with this dx. So you still have 1/4 for the entire integral. So I have 1/4 integral of cosine of 2x times 2 dx. Okay, ginsulod ko di ang 2 ho para siya ang ma-represent sang du sining 2x. So 2 dx. This one will have 1/4. Now this is the squared of 2x. So we need to write the equivalent identity of cosine squared here, which is another 1/2, 1, since it's cosine, plus cosine of what? So this is 2x, it will double here, it will become 4x. Okay? So this is the integral that you need to process. dx. I'll write in here para clear because there you have the correction already of 1/4. So for that one, I'll write here that would be 1/4 x. For this one, this is already cosine of u du. This entire thing is du. So then the answer of the cosine is sine u, right? So sine of 2x. Because if you will differentiate it, that would be cosine of 2x. So I'll write here plus 1/4 sine of 2x. The integral of cosine 2x. This 1/4, if multiplied to this 1/2, will be 1/8. So I'll write here plus 1/8 x. Why? Because the integral of that would simply be an x. Now this one will need a 4, right? It will need a 4 dx here, so that would be 1/4. So I will place here plus, so this is already 1/8. This one will need 1/4. So 1/8 plus 1/4, this is already 1/8 plus 1/4 for the derivative of this one, that would be 1/32. Cosine will have an integral of sine 4x plus c. If you're going to have this combined, the 1/4 and the 1/8, that would be 3/8. So this should be 3/8. 1/4 sine of 2x should be here, should have a 4 in the denominator, and this one should be 1/32 sine of 4x because of this which was not squared in here. Okay? So remember, we converted the cosine squared of 2x into its equivalent double angle cosine. So if you get its double angle cosine, that would be 1 plus, you double this angle, cosine of 4x. It's plus because it's cosine. This is always the denominator. So this one, 1/2 times 1/4, that would be 1/8x. And this 1/8 cosine of 4x will be 1/32 sine of 4x, because you need to have the derivative of 4x here, which is 4dx, which requires that you divide by 4 again. So 1/8 times 1/4, that would be 1/32 sine of 4x. We will cover the rest of this topic on Thursday. Thursday for types 2 to 6. Hopefully, we can cover until 6. Your next quiz will be given next week naman. So I'll give you a quiz next week on Module 2, but we will have it sliced because I don't want you to have a very long quiz. So we'll slice it per topic. Okay, before we part ways, do you have any questions? You have any questions here? Okay, go back to this because it's in your Canvas anyhow. You can check that. It's available in your Canvas. I'll stop sharing.